This video is about two tools from theoretical computer science. The first tool is Deterministic Finite Automata, abbreviated as DFA. DFAs are an abstract model of machines that process strings symbol by following simple rules. The second tool is regular expressions. These allow us to elegantly describe certain patterns in strings, and they are an essential tool for software developers. At first glance, these two tools don't seem to have much in common, but it turns out there's a surprising connection between them and even many more tools. By the way, you don't need any prior knowledge of theoretical computer science. We'll go through everything step by step, starting with DFAs. In theoretical computer science, we talk about computers. But what exactly is a computer? When we hear the word computer, we probably first think of something with a keyboard, a screen, and so on. But that's not what we mean here. Instead, we are interested in abstract models of computers. What defines a computer at its core? It performs computations. It receives some input, carries out a computation, and produces an output. That's why we prefer to talk about so-called models of computation. One of the simplest models of computation is a so-called DFA, which stands for Deterministic Finite Automaton. A DFA receives a string as input, which is a sequence of symbols. It reads the string symbol by symbol and follows certain instructions. When it has finished reading the string, it gives an output, either true or false. Instead of true and false, we often speak of accepting and rejecting. More precisely, a DFA consists of a finite number of states, which we draw as circles. One state is labeled as the initial state, and any subset of the states is labeled as accepting, here indicated by pink circles. The arrows are called transitions, and from every state we need exactly one outgoing arrow for each possible symbol in our input strings. For the sake of simplicity, let's assume that our strings only contain the symbols A and B. To process an input string, we begin in the initial state, then read the input string symbol by symbol and follow the arrows until we have finished reading the string. The state where we end up indicates whether we accept or reject the string. If we are in an accepting state, the string is accepted. Otherwise, it is rejected. Can you describe in one sentence which strings are accepted by this DFA? Perhaps pause the video briefly to think about it. The answer: this DFA accepts all strings that contain AB as a substring. That means every string with substring AB is accepted and every string without substring AB is rejected. And just like this, every DFA defines a language. In the parlance of theoretical computer science, a language is just a set of strings. And the language recognized by a DFA is the set of all strings that it accepts. Here's another example. What language does this DFA recognize? Pause the video for a moment to think about it. The answer is all strings with an even number of A's. If you've never seen DFAs before, I recommend you play around with this concept a little more. Here are some more exercises for you. DFAs are obviously a very simple model of computation. There's a huge number of such models, and DFAs live at the lower end in terms of expressive power, in the sense that there are many languages that cannot be recognized by any DFA. Here's an example. All strings that have exactly the same number of A's and B's. Well, it's easy to write, let's say, a Python program for this language. It can be proven that there is no DFA that recognizes this language. The intuitive reason is that a DFA only has a limited memory. It only knows which state it is currently in and therefore cannot memorize arbitrarily large numbers. In summary, DFAs are a very simple model of computation for processing strings. Each DFA defines a language, namely the set of all strings that it accepts. And there are languages that can be recognized by DFAs, and there are also languages that cannot be recognized by any DFA. Regular expressions, or regex for short, are a useful tool in computer science and programming to describe strings that follow a certain pattern. Example: every email address starts with some alphanumeric symbols, then an @ symbol, then some more alphanumeric symbols, then a dot, and then some more alphanumeric symbols. Or addresses in Germany usually have a 5-digit zip code, followed by a space, followed by an uppercase letter, and then followed by some lowercase letters for the name of the city. Regular expressions can be used to describe such patterns. Here's an example of a regular expression for all strings consisting of the symbols A and B that contain the substring BB at least once and end in A. We can see the BB in the middle, the A at the end, and in between there's always this A plus B star, which stands for an arbitrary sequence of A's and B's. We then say this regular expression matches this or that string. For example, this expression matches the string ABA BB AA. But how do regular expressions work in detail? Let's break it down. The simplest regular expressions are single symbols. A single A is a regular expression, and this expression matches exactly one string, namely the string A. Now there are 3 operations we can use to build new regular expressions from existing ones. First, union. If we write a plus in between 2 regular expressions, the resulting regex describes the union of the languages of the 2 sub-expressions. That is, it matches all strings of the first expression and all strings of the second expression. For example, A plus B matches the string A as well as the string B. Second, concatenation. This is the technical term for writing things back to back. When we write 2 regular expressions directly one after another, the resulting regex matches every string that can be formed by taking a string matched by the first regex and immediately appending a string matched by the second. For example, A plus B, C matches both AC and BC. And third, the Kleene star. A star around a regex means that this regex can be concatenated with itself any number of times. For example, A star stands for a sequence of A's of any length. So the regex A star matches the following strings. Repeating it 0 times is explicitly permitted here, which then corresponds to the empty string. To avoid writing quotation marks, we denote the empty string by the Greek letter epsilon. Another example, A plus B star matches all strings that we can form by concatenating an A or a B as often as we like. In other words, these are all strings that can be formed using only A's and B's. Let's try to build a regex for all strings made of A's and B's that have an even number of A's. Let's start by building a regex for all strings with exactly 2 A's. B star, A, B star, A, B star. We now want to repeat such strings as often as we like, so we add another Kleene star around it. Almost done. But what about 0 A's? 0 is also an even number, but strings that only have B's and no A's are still missing. Therefore, we add plus B star at the end. So we can also match strings that only consist of B's. This gives us our final regex for all strings that have an even number of A's. Let's test whether the expression actually works. Here's a string with an even number of a's. To match the string, we must first select an alternative, either the long expression on the left or the b star on the right. We opt for the long expression. This has a Kleene star, so we can repeat the inner expression as often as we like. We repeat it twice and split our string so that the first and second part each have 2 a's. Now we can easily finish our match. One small technical detail. We allow 2 more special regular expressions, namely epsilon and the empty set. Epsilon is a regular expression that matches exactly one string, namely the empty string. And the empty set is a regular expression that does not match any string at all, so it does not even match the empty string. We can combine epsilon and the empty set with other regular expressions as usual. For example, the expression a plus epsilon b matches the string ab as well as a single b. Summary. Regular expressions are a tool for describing certain strings. Each regex defines a language. The language defined by a regular expression is the set of all strings to which the expression matches. Here again some exercises. We've now seen 2 tools for describing languages. On the one hand, DFAs that process a string from front to back, symbol by symbol, passing through states. And on the other hand, regular expressions that assemble strings from certain operations, such as union and concatenation. At first glance, these 2 tools do not seem to have much in common. And yet, the following surprising result holds. The languages that can be recognized by DFAs are exactly the same as those that can be described by regular expressions. This means for every DFA, there is a regex that matches exactly the strings that the DFA accepts. And vice versa, for every regex, there is a DFA that accepts exactly those strings that the regex matches. We've already seen one example for a language that can be described by both a DFA and a regex. But the fact that DFAs and regular expressions have such a strong connection is a little unexpected, isn't it? DFAs can be very complex. We can jump back and forth between states, like in spaghetti code. Regular expressions, on the other hand, describe strings very sequentially. First there must be this symbol, then that one, then this part is repeated, and so on. To prove the theorem, we need to show 2 directions. First, a translation of DFAs into regular expressions, and second, a translation of regular expressions into DFAs. Both proof directions are really interesting and need quite clever ideas. I only want to show one of the proof directions in this video, namely from DFA to regex. We might do the other proof direction in one of the next videos. Let's take any DFA. How can we show that there is a regular expression that matches exactly those strings that the DFA accepts? This is not obvious at first, but here's a very nice proof strategy that is often found in mathematics, namely, we make the problem more general to make it simpler. The actual question is, what does a regular expression look like for all strings that take us from the starting state to the accepting state? We can generalize this question, for example, what does a regular expression look like for all strings that take us from state P to state Q for all possible states P and Q? This is no longer just one question, but it's 9 questions, since we have 3 possibilities for each P and Q in this case. Okay, none of these questions seem any easier than our original question. But let's make the problem even more general. This is getting a bit crazy now, but let's just ask the following. which strings get us from state P to state Q if we are only allowed to visit the first m states of the DFA in between on the way from P to Q. Here m is a number between 0 and 3. The 9 questions from before are the cases for m equals 3, that is, where we are allowed to visit the first 3, which is all of the states of our DFA. But if we choose a smaller number m, then other questions arise. For example, for m equals 2, p equals 3 and q equals 1, which strings take us from state 3 to state 1, where we may only use the first 2 states in between. So we start in state 3, we end in state 1, but every other state we visit in between may only be state 1 or state 2. An example would be the string ABAAA, because the intermediate states are only states 1 and 2. The string BAB, on the other hand, would not be allowed, because state 3 would then also appear as an intermediate state. Okay, but why do we do all of this? Why are we asking so many complicated questions? We now make 3 important observations. First observation. One of these questions is still exactly the one we are actually interested in, namely P, the starting state, Q, the accepting state, and m equals 3. These are exactly the strings that the DFA accepts. The second observation. Some of these questions are not so complicated. On the contrary, they are very easy to answer. If m equals 0, then we want to go from some state P to some state Q and are not allowed to visit any states in between. Well, these are simply the arrows that lead directly from P to Q, if there are any such arrows. In those cases, we can immediately write down a regex, and thus we can fill in the column for m equals 0 easily. And now the third observation, and this is the crucial one. If we found all regular expressions for the cases m equals 0, then we can use those to construct the regular expressions for the cases m equals 1. And from these, in turn, we can then construct the regular expressions for m equals 2, and so on. Let's take a closer look at this, and let's introduce a notation. Namely, let R with lower index p, q and upper index m be the regular expression for all strings that take us from state P to state Q, visiting only the first m states in between. We already got all regular expressions for the cases m equals 0, and now we are looking at a case where m equals 1. For example, R, 2, 3, 1. That is a regular expression for all strings that take us from state 2 to state 3, and in between may only use state number 1. But may does not mean must, so one possibility is that we go directly from state 2 to state 3 without using state 1 in between. This is exactly the regex R230, which is simply A. The other possibility is that we go from state 2 to state 3 while using state 1 as an intermediate state. But each such string can be split into several segments that do not use state 1 as an intermediate state. We first go from state 2 to state 1 without using state 1 in between. This is R210, which is the regex B. We can then loop in state 1 as many times as we like, but this can be expressed as R110 star, that is the transitions from state 1 to state 1, and then the Kleene star around it to repeat such strings any number of times. In our example, this comes out to be A star. And finally, we need to get from state 1 to state 3, that is R130. In our example, this is just B. Now we have assembled the regex R231 from regexes that all come from the column for m equals 0. And this procedure works in general. The regular expressions for column m+1 can always be composed of regular expressions from column m. Using this method, we can fill the table column by column until we obtain our desired regex. The expressions can quickly become very long, so we simplify them as much as we can after each step. And finally, we obtain the regex that matches exactly those strings that the DFA accepts. This procedure works for every DFA, so now we know that every DFA can be translated into a regex. Just to summarize the core idea of the proof again, we phrased our original question much more generally, so instead of one question, we suddenly had a lot of questions to answer. But among those questions, some of them were very easy to answer, and the answers to the more complex ones can be put together from the answers to the simpler questions. This principle is called induction. That is, we first proved our statement for the case m equals 0, and then we showed that if the statement is already true for any number m, then it is also true for m+1. Okay, that was the technical deep dive of the video. Now let's zoom out again and put things into context. We've seen that for every language that is recognized by a DFA, there is a regex that describes exactly the same language. This is the first piece of a big puzzle. The next piece would be a proof in the opposite direction. For every regex, there is a DFA that describes exactly the same language. This statement is true as well, but we've not proven it here. With this statement, we would then know that regular expressions and DFA can describe exactly the same languages, meaning that they have exactly the same expressive power. But is that actually interesting? In fact, there are many more things that describe exactly the same languages. Many formalisms, including various automata, regular expressions, grammars and logics, etc., all describe exactly the same languages. So it's a very robust concept. And that's why it gets its own name, the regular languages. Each of these tools can help us to get a better understanding of regular languages, and it is often helpful to switch back and forth between the different perspectives. Here's an example. Let's imagine we really dislike Swedish pop bands from the 1970s, and we therefore need a regex for strings in which the sequence ABBA does not occur. At first glance, this seems a bit weird. After all, regular expressions are made to match on strings. But how can we match on strings that do not contain a certain substring? What can we match on in this case? A regex for the opposite would be very simple. A plus B star, ABBA, A plus B star. This regex matches all strings that do contain the substring ABBA, but that is exactly the opposite of what we are looking for. Does such a regex even exist? The answer is yes. We can first translate this regex into a DFA using the method that I didn't show in this video. A DFA is very easy to complement. We simply swap accepting and rejecting states. Then the DFA accepts exactly those strings that do not contain the substring ABBA. And then we translate this DFA back into a regex using the procedure we've just seen. To conclude, I would like to briefly summarize the key takeaways. First, regular languages are a robust concept that appears in many different subfields of theoretical computer science. We've only looked at 2 tools related to regular languages in this video, but there are many more, and there's a lot to say about each one, because each one provides a new perspective on the central concept. And secondly, we saw 2 common proof strategies. One was generalization. It was helpful to generalize the problem and look at many similar questions at the same time. Then we used another strategy, namely induction. We were able to use the solutions of the sub-questions to build the solutions to the more complicated questions. I hope the explanations were clear. If you enjoyed the video, please leave a like or comment, and subscribe to the channel if you're interested in more videos of this kind.